Hello, and welcome to the first module of the DJI Zenmuse L1 training course. This module forms part of an informative series aimed to provide you with a comprehensive understanding of the Zenmuse L1. Throughout the course, you will begin to understand the best practices used to obtain good quality and accurate data from your LiDAR surveys. Given the nature of LiDAR, there will be guidance on all steps, including hardware preparation, mission planning, mission monitoring, data processing, and sensor calibration. There are no prerequisites to this course, however feel free to pause and research specific areas if you would like to understand the underlying principles in greater detail. Importantly, this course has been designed to provide you with the ability to obtain data that is both good quality and accurate without any previous experience with LiDAR data. If you have used LiDAR units in the past or worked with the data closely, then you may notice that some steps are very similar to other systems and workflows. Before collecting data, it is very important to know what the system can and can't do, and likewise what components are involved with the unit itself. Our first module will aim to provide us with a familiarisation of the characteristics of the sensor and the technical specification of the hardware and software involved. Firstly, we can take a look at the hard case used to protect and transport the Zenmuse L1. Given the nature of the highly accurate LiDAR unit, it is crucial that the hardware is protected appropriately. As such, DJI provides a hard shell style pally case to keep the unit protected from any direct knocks. However, it is important to note that the L1 hard case should still be kept secure when in transportation to ensure that your unit does not experience any drops or falls. This is important because the L1 is heavily reliant on a self-contained, high-accurate inertial measurement unit that is used to accurately determine the directional movement of the unit when in flight. As the IMU data is used when processing your data, it is essential that the IMU is working to its best effect. Likewise, in order to protect the L1 from the elements, the hard case is also IP67 rated, meaning it is fully waterproof. Taking a closer look inside of the box, we can first see the unit is secured by foam inserts, alongside the accessories also contained within the package. Again, this further improves the security of the precision system. The first item we come across is a 6-month free trial to DJI Terra. DJI Terra is the software used to process your raw data from the L1 in order to develop a fully calibrated and optimized point cloud. DJI Terra also provides the ability to perform some very basic analysis, customization of your point cloud, and adjustment to the coordinate system your data lies within. We will take an in-depth look into the DJI Terra platform in a later module, as it is a crucial part of the workflow. Inside of the same foam slot, we also have the product certification and quick start guide. The product certification is something that is required for most electronic equipment used in Europe, which certifies compliance with a number of directives, for example, electronic waste. Likewise, the quick start guide is also included in the foam slot, providing you with a hard copy of the manual illustrating basic operations. However, it does not provide any detail on workflows or data collection. Towards the back of the hard case, you will also find a lens cloth, used to wipe down the lens of both the LiDAR reflective sensor and the RGB camera sensor. Photogrammetric and LiDAR data outputs are very reliant on the high resolution and good quality data. Therefore, any marks or particles on the sensor can significantly affect the output, even if very small. Every couple of months, it is recommended that you replace the lens cloth to ensure that you are not further damaging the sensor with any embedded particles. If your cloth becomes dirty or wet, always replace it to ensure your lens does not become damaged. Now, let's take a look at the sensor itself. The Zenmuse L1 comes as part of a 3-axis gimbal, allowing for greater usability in enclosed environments. As you can see, the sensor can rotate freely on the system when it is not connected to the aircraft. This is normal. A lot like other DJI gimbals, the L1 also uses a Skyport connection, meaning it is directly integrated with the corresponding gimbal connector on the Matrice 300 RTK. In a later module, we will provide a demonstration of how to connect the unit to the Skyport on the aircraft. To protect the Skyport, a gimbal connector is also provided. Likewise, as we take a look at the front of the gimbal, you will also find a rubberized lens protector, used to further protect the sensor itself. As the L1 reflective sensor is made of glass, it is important to always place the lens protector back onto the unit when finished capturing data. If it is your first time opening the package, you will also find a protective sticker on the reflective sensor. Please remove this in preparation for your first flight. This sticker may be kept and replaced for further and ongoing protection. However, your main protection comes from the rubberized lens, so please do not worry if the sticker becomes unusable. The L1 sensor itself is in fact from the LiVox sensor range. Beneath the LiDAR sensor, we have a 1-inch CMOS sensor, representing the same specification as the Phantom 4 RTK photogrammetry solution. This can be used as a standalone photogrammetric or photography solution, or in order to provide a colorized LiDAR point cloud. The third sensor, located at the bottom right of the payload, is a camera used specifically for vision positioning and to maintain a degree of accuracy if there is a loss of GNSS signal. However, this is for fail-safe only and is only recommended to operate with a GNSS signal. Inside of the unit itself is where you would find the IMU, which helps to form the fully integrated surveying LiDAR unit that DJI have developed. For data storage purposes, you will find a micro SD card slot on the side of the sensor. We will provide you with more detail on the recommended cards in the next section. This now completes our introduction to the sensor characteristics, and we will now move on to the technical specifications of the system that directly relate to the data that you should expect to collect. The diagram on screen provides an illustration of the Zenmuse L1 and the components that have been used to develop the integrated mapping solution. In order to provide you with full oversight of how the system works, we will break down each component individually. The first component we come to is the gimbal connector. As previously mentioned, this uses the DJI Skyport connector. Similar to other DJI payloads, the Skyport is connected to the aircraft through a quarter turn until the two red dots align. This is something that we will visually illustrate in a later module. The next component is the pan motor, used to orientate the gimbal from left to right. Whilst there is a definitive extent to which the payload can pan, you can fully orientate beyond 180 degrees either way. This means you have a visibility around a full 360 degrees. The third component is the LiDAR itself. The LiDAR sensor is a green glass sensor on the front of your payload that is used to emit and receive returned laser beams that are used for direct measurements of points of the area of interest. Essentially, the time difference between the laser emittance and it being received is measured in order to calculate the location of a point in a point cloud. It is important that the reflective surface stays reflective to ensure as much data is recorded as possible. As discussed in the unboxing video, the sensor also holds a standard RGB camera that represents the same specification as the Phantom 4 RTK and can be used for photogrammetric purposes. However, in tandem with the LiDAR sensor, it can also be used to generate colorized point clouds. Item number 5 relates to the auxiliary positioning vision sensor is used to assist the drone when GNSS systems are not recording to full effect. It is also used to help position the drone when the aircraft is landing. Located on the bottom left-hand corner of the right side of your payload, you will find the micro SD card slot. A lot like other Matrice 300 RTK payloads, the SD card is micro-sized, with the Zenmuse P1 being the only other payload that requires a normal-sized SD card. As standard, you will receive a 64GB SD card with your L1 for data capture purposes. However, if you wish to use a larger SD card, you can do so, but please make sure that the SD card can write quick enough for L1 data capture. Our 7th marker on our diagram illustrates the location of the tilt motor, which is found on the right-hand side of the payload. The tilt motor is the second axis of a 3-axis gimbal and allows the payload to tilt forward and backward, which is especially useful for nadir and oblique data capture applications. The final component of the Zenmuse L1 is the roll motor and allows for the gimbal to rotate left and right. In combination with the tilt motor, this can also assist with operating the payload at oblique camera angles. That completes the 3-axis gimbal setup of the Zenmuse L1 and likewise concludes the breakdown of the L1's visible components. The IMU is located inside of the main L1 unit and is the component that requires calibration before, during and after the flight. Therefore, we will take a closer look at how to do this in a later module. In the next part of this module, we will take a brief look at the technical specifications of the Zenmuse L1. The unit itself is a little over 15 centimeters in length, 11 centimeters in width and nearly 17 centimeters in depth, whilst also weighing 930 grams, making it a compact and lightweight LiDAR solution. As standard, the Zenmuse L1 will use around 30 watt of power during flight. However, this can rise up to a maximum of 60 watt during high-intensity missions. Whilst the L1 does not have an internal battery, it pulls power from the TB60 intelligent flight batteries housed on the Matrice 300 RTK. Like the M300 RTK, the Zenmuse L1 also holds an ingress protection rating, but instead of IP45, it holds an IP54 rating. To break this down, the first figure relates to intrusion protection, and with a rating of 5, this means that the unit is protected against dust-limited ingress, no harmful deposits. The second figure relates to moisture protection, and with a rating of 4, this means that the unit is protected against water splash from all directions. Limited ingress permitted. Although not completely protected, the Zenmuse L1 has significant protection against both intrusion and moisture, meaning missions in more adverse weather conditions are possible, although it is still important to consider how such weather conditions will affect your data. The operating temperature of the Zenmuse L1 LiDAR sensor is between -20 degrees and 50 degrees Celsius. However, the RGB sensor is slightly more stringent, with a warmer bottom bracket of 0 degrees Celsius, but with the same upper bracket. The storage temperature, on the other hand, holds an operating bracket between -20 degrees and 60 degrees Celsius. Moving on to system performance, we can first look at the detection range, which refers to the farthest measurable distance of the LiDAR. A surface with a reflectivity of 80% will allow for detection up to 450 meters under zero klaxon, also known as solar illumination. A surface with a 10% reflectivity will allow for detection up to a range of 190 meters under illumination of 100 klaxon. The main influencing factors include the target's surface reflectivity, the target shape, and ambient light interference. Most LiDAR sensors on the market use diffuse reflection objects as their testing benchmark. However, this parameter has limited practical significance. The measurable distance at a reflectivity of 10% has greater practical significance. In many applications, there are varied reflectivity, therefore lower flights are recommended. We will cover this in more detail later in the course. The Zenmuse L1 can be flown with a different number of return measurements per laser output, which directly affects your point sample rate, amongst other things such as flight speed and height. When using the L1 with a single return rate, you can expect to obtain a maximum of 240,000 points per second, whereas with a dual or triple return, you can expect up to 480,000 points per second. It is recommended to choose dual echo mode if you need more measured points, or choose triple echo mode if you need higher penetration. Although accuracy depends on a number of variables, the Zenmuse L1 is capable of achieving an accuracy of at least 10 cm in the horizontal and 5 cm in the vertical when flying at 50 meters. DJI have validated this to an accuracy of 1 sigma, meaning a 68% likelihood. During flight, the Enterprise Smart Controller supports real-time point cloud colouring, allowing you to watch your data construct live. As standard, you can view your point cloud by reflectivity, height and distance. However, if RGB colouring is enabled, you can also view in this mode. Looking more closely at the LiDAR itself, it holds a range and accuracy of 3 cm at 100 meters, which, as opposed to the system accuracy, refers to the relative measurement between the sensor and an arbitrary point. When working in a multiple scanning mode, the Zenmuse L1 can achieve up to triple returns. As LiDAR sensors emit laser beams, it is crucial to understand whether they can be harmful. In this case of the Zenmuse L1, it falls into Class 1, which is safe under all conditions and normal use, therefore no concerns. Field of view, also known as scan angle, represents the angle covered by the LiDAR sensor, or the angle at which laser signals are emitted. Given the nature of different scanning patterns, the vertical field of view is different for each type whilst the horizontal remains the same at 70.4 degrees. For a non-repetitive scanning pattern, your vertical field of view will be 77.2 degrees, whereas a repetitive pattern would have a far smaller 4.5 degrees. A repetitive scanning pattern is particularly useful for topographical surveying, when accuracy is of the most importance, and a non-repetitive generates a greater point cloud density but with a slightly reduced accuracy, particularly good for urban reconstructions. Whilst the inertial navigation system is something you cannot control nor affect, we will take a quick look at the specification it holds, all of which is crucial in the capture of highly accurate data. An IMU update frequency of 200 Hz, an accelerometer range of plus or minus 8 G, an angular velocity meter range of plus or minus 2000 degrees per second, a yaw accuracy of 0.3 degrees in real time, and 0.1.5 degrees through post-processing in DJI Terra, this is the accuracy to 1 sigma or 68%. A pitch and roll accuracy in real time of 0.05 degrees and 0.025 degrees through post-processing in DJI Terra. Again, this is to an accuracy of 1 sigma or 68%. The auxiliary positioning vision sensor holds a resolution of 1280 by 960 with a field of view of 95 degrees. This is not used for data capture purposes, so high resolution is not required. The RGB mapping camera situated on the base of the Zenmuse L1 is the equivalent to the specification of the Phantom 4 RTK. The 1-inch sensor holds an effective 20 megapixels, allowing for the following variations of high-resolution image collection with different aspect ratios: 5472 by 3078 pixels in a 16 by 9 aspect ratio, 4864 by 3648 pixels in a 4 by 3 aspect ratio, 5472 by 3648 pixels in a 3 by 2 aspect ratio. At a 1-inch sensor size, the RGB camera on the L1 holds an 8.8 focal length. However, this is equivalent to a 24mm focal length in relation to a full-frame sensor. The adjustable ISO range allows for a level between 100 and 3200 when in automatic mode for both photo and video. When in manual mode, this increases to 6400 for video and 12800 for photo. The sensor has an aperture range of f2.8 to f11. For image storage, the sensor supports the standardized FAT file systems. For data output, the sensor records images in JPEG only and videos in MOV and MP4. Unlike many LiDARs, the Zenmuse L1 operates on a stabilized gimbal system, allowing for a 3-axis movement: tilting forward and backward, roll around its axis, and pan from left to right. The gimbal itself has an angular vibration of 0.01 degrees and is attached to the Matrice 300 via a detachable skyport. When mounted to the aircraft and in flight, the axis allows for a tilt range from -120 degrees through to +30 degrees, and a pan of +320 degrees, something that is unique to the L1. In different operating modes, the gimbal can be used in follow and free mode. When using the Zenmuse L1 for LiDAR data capture, it will produce a series of files all stored in one folder. The folder contains files relating to the RGB photos, IMU, point cloud data, GNSS observations, and calibration files. We will provide more details on the different files later in the course. As a result of the amount of data captured, and in particular the raw LiDAR, the Zenmuse L1 requires a certain specification of SD card in order for the system to write quick enough. If the SD card is too slow, then your data will not be captured. As such, DJI recommends a microSD with a sequential writing speed of 50 megabytes per second or above, and a UHS-1 speed grade 3 rating or above. The max capacity of the said SD card will be 256 gigabytes. DJI also recommends the following SD cards: SanDisk Extreme, 16 GB to 128 GB, UHS-1, speed grade 3. Lexar 1066X, 128 GB U3, and the Samsung Evo Plus 128 GB. Finally, the Zenmuse L1 data fundamentally requires processing before it can be interpreted. Therefore, your data will need to be processed through DJI Terra in order to obtain a point cloud. Once processed, DJI Terra can provide the following standardized formats: PNTS, LAS, PLY, PCD, S3MB. This brings us to the end of the first section of the L1 workflow course. You should now be familiar with the sensor itself and the functionality available through the technical specification. Our next section will introduce you to the workflows that can be employed by the Zenmuse L1 in order to optimize the accuracies of your datasets.